Okay, kids, so what we're going to do today is continue on in section 3.4, and we're solving more complex friction problems. Now, more complex friction problems are called that because they're actually a combination of looking at the world of dynamics, which is all about forces, the causes of motion, the causes of changes of motion, and kinematics, just the motion itself. It brings these two parts of our course together. So this is really the peak of chapter 1, chapter 2, chapter 3 all coming together. So there's what I'm going to show you now is sort of an underlying strategy, an underlying structure that you can use when you're solving these more complex friction problems, more complex dynamics problems in general, really. So the key to this is understanding that the quantity acceleration is the only quantity that's found on both sides. Look, it's here. Acceleration, acceleration, acceleration. Here we go. Come on. Acceleration. It's on both sides, okay? Because it's also over here. F net equals ma, the most important equation in physics, along with its companion equation. So when you're solving these more complex dynamics problems, uh, one of two things can happen. You can either be given a whole bunch of kinematics information, given information like final velocity or initial velocity or time or displacement, and somehow, some way you use it to find acceleration, and then you can bring the acceleration over to here and use it to find a variety of different forces. That's one type of problem you may run into. The other type of problem, the second of two possible things, is you're given a whole bunch of dynamics information, a whole bunch of given dynamics information, maybe something about friction or normal force or other forces acting on an object. And then the whole goal here is to find F net, which will allow you to find acceleration. Then you can bring acceleration over to this side and use it with other pieces of given information to find some kinematics quantity like initial velocity, final velocity, time, displacement, what have you. But this little diagram here is basically the underlying structure, the way, the strategy to approach a lot of these more complex dynamics problems. So a good place to start is just to take a look at a sample problem. Now we're going to look at sample problem number 3. It's on page 104 from section 3.4. And we're going to use grass. Okay. So it says a 0.17, excuse me, let me restart. A 0.17 kilogram hockey puck. So here's the hockey puck, and we know the mass is sliding on an outdoor rink and has an initial velocity of 19 meters per second forward. Don't like forward, going to make it positive, right? When it suddenly hits a rough patch of ice that is 5.1 meters across, assume that the coefficient of kinetic friction between the puck and the rough ice is 0.47. Remember, coefficients of friction are unitless. So it says, draw yourself some diagrams so you can figure out what's going on here. And that's exactly what I've done right here. So this is positive x direction. The object is moving forward. Here's the puck. There's the normal force acting on the puck. Okay, right back at it. The normal force acting on the object, the weight or the force of gravity acting on the object is there. And then we have the force of kinetic friction. And these are all known equations. Normal force is always equal to the negative force of gravity. Weight, force of gravity is equal to mass times the gravitational field strength near the surface of the Earth. And the magnitude of force of kinetic friction is equal to the coefficient of kinetic friction times the magnitude of the normal force. These are all known equations. Then I'm going to draw a little picture of what's actually happening. Here, green, I got smooth ice on the other end. And here's the rough patch, which I've kind of drawn in purpley. And the coefficient of kinetic friction there is 0.47 right in here. And this puck comes in moving at positive 19 meters per second, boom, and then it hits the rough patch and it stays in the rough patch for positive 5.1 meters. So that positive 5.1 meters becomes the displacement for this question. It becomes the displacement of the object in the rough patch. Okay, so one of the things that they want us to solve for here is the frictional force, the kinetic frictional force right there. So there's our required. Well, gee, how would I go about figuring that out? Well, hey, I have an equation right there, so I'm going to use it. I'll rewrite the equation. The magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction times the magnitude of the normal force. And next line, we know that the normal force is equal in magnitude but opposite in direction to the force of gravity. And the next line, we know that the force of gravity is equal to the mass of the object times the gravitational field strength near the surface of the Earth. These are all known quantities, they're all in our given. So I can now substitute and I plug in the numbers, and lo and behold, I get that the magnitude of the force of kinetic friction is 0.78 newtons. Of course, forces are always in newton. A little word to remind you here that the coefficients are always unitless, okay? Please remember that. Now, this only allowed us to calculate the magnitude of the force of kinetic friction, but we were asked for the entire vector, including direction. Well, the direction comes from the free body diagram. Boom, it's backwards, it's negative x. So I can say that the force of kinetic friction is negative 0.78 newtons. All right, and next they wanted us to calculate the acceleration, so required acceleration. And when you see acceleration being asked for and you have in your mind a whole bunch of information has been given to you about forces, that should be a clue to you. I got a bunch of information about forces. I've drawn a free body diagram. If I'm going to find acceleration, I need to use the most important equation in physics, F net equals ma, and its companion equation, F net is the sum of all forces. And remember that this is really the key that unlocks so many dynamics problems. So I write them out. F net equals ma, and F net is the sum of all forces. I go to the free body diagram, and I see that there are only three forces acting on this object: the force of kinetic friction, the normal force, and the force of gravity. And as we've done so many times in the past, the normal force and the force of gravity cancel each other out. Bingo, bango, they're gone. So that just leaves us with the net force equals the force of kinetic friction, which we can slide over to the companion equation right here and replace F net with force of kinetic friction. Therefore, the force of kinetic friction is equal to the mass of the object times its acceleration. We rearrange this in order to solve for acceleration, and we get acceleration is equal to the force of kinetic friction divided by the mass. Now, these are all quantities that we now know. We just solved for this, force of kinetic friction. We knew the mass, so we do a little dividing with our calculator, and we get that the acceleration is negative 4.6 newtons per kilogram, but no one writes it like that. A few weeks ago, I showed you how newtons per kilogram is equivalent to the more standard way of reporting a unit for acceleration, meters per second squared. So the solution is the acceleration of the puck is negative 4.6 meters per second squared. Now, the next thing they wanted us to solve for was how fast is that puck moving when it just gets to the end of the rough patch and starts out again on the smooth ice? Well, that means we want to find final velocity. So therefore, it required final velocity. Now I have to go to my list of kinematics equations and find a kinematics equation that will let me calculate final velocity with the set of information that I'm given. All right? Well, I was given the initial velocity. All right? I was given the initial velocity. I was given the displacement on the ice. And like many of these dynamics problems, I worked over in with the force equations, with the dynamics equations. I did some work there, and I was able to find acceleration and now bring it into a kinematics problem equation. So I rearranged this. We've done this many times in class, just like that. I rearranged it to this. I can now substitute in the values. The object was moving at 19 meters per second positive to begin with before it got into the rough patch. The acceleration within the rough patch I calculated through dynamics equations. Now I'm bringing it into a kinematics equation, and the displacement was known. The displacement was known right there. So I plug in those values and I have a final velocity of 18 meters per second, and it's still moving forward, still positive. So it didn't really slow down by that much. It's still ice, it's just rough ice. So there was a little bit of slowing down. Okay, so now we're going to try section 3.4, practice question 8. It's on that same page there, but we're going to actually try this. Now listen, take some advice from me. Try this question on your own first. Maybe you won't get all the way through. That's all right. Struggle through it. Struggle is good. Make mistakes. Learn from them. Be patient with yourself. All right? But if you really want to get some learning out of trying this example here, try it yourself first. Pause this video. Try it. See how far you get. Then restart the video and then look and follow through the video. Now I will provide my solution. Okay? If you just continue watching the video, oh yeah, that's how you do it, I get it, your learning won't be as strong. Okay? Remember, we learn through struggle. All right? All right, so I assume everybody tried this question, and now you're just going to come along for the ride to see how we're going to solve it together. Get it? Come along for a ride because it's a car ride. So, in a brake test on dry asphalt, a Chevrolet Camaro traveling with an initial speed of 26.8 meters per second. Okay, so look, I've drawn a diagram down here in my given. What's up, G? G for given. And look, I've put in here a little picture. Here's the car. Okay, it's a Camaro. It's a sports car. See, it's aerodynamic. And its initial velocity, positive 26.8 meters per second. We're going to use positive. And then it moves forward, okay, till it stops. So look what it says here. Had an initial speed of 26.8 meters per second, can stop without skidding after moving 39.3 meters. What's this all mean? It means it moves forward while it's braking, and it moves forward for 39.3 meters until it eventually comes to a stop, meaning at this point right here, its final velocity is 0. That's what all of this uh, meant up here. I've converted this into a picture. Remember, we have to draw a picture. It really helps us. So let's continue here. In my G, I've also drawn a free body diagram. And on this car is the weight or the force of gravity. Let me fix that. I made a wee error there. So let me fix that. That's not the normal force. Here we have it. Put a G there. What's up, G? Okay, so there's the force of gravity, also known as weight, equal the mass of the object times the gravitational field strength near the surface of the Earth. Up here is the normal force, which is equal in magnitude but opposite in direction to the force of gravity. And then over here we have a force of rolling friction. Now this is a little bit different than the force of kinetic friction or the force of static friction. The wheels keep turning while the car stops. So it's a different kind of friction. We're going to call it force rolling friction right there. And now we have drawn our free body diagram. We've drawn a little diagram to show what's happening, and we're ready to solve what we're being asked to solve for. So it says here, determine the magnitude of the average acceleration of the car during the non-skidding braking. Okay? So as I'm looking at this, I'm saying they want me to calculate acceleration. And look, I've been given a lot of kinematics information. Initial velocity, final velocity, displacement. So if I've been given all of this kinematics information, I bet you I can solve acceleration by using a kinematics equation, and I can. But that was the clue. So here's what I've done. Okay? Required in part A is the acceleration. I'm going to use this equation right here. Standard kinematics equation. I'm going to rearrange this equation for acceleration. And we've done this before in class. I've rearranged it, but if some of you like substituting to solve for this, go right ahead. No problem. So I've substituted in my values right here. substituted in my values, and I got an acceleration of negative 9.14 meters per second squared. It's slowing down, the acceleration is negative, and now we have solved part A of this problem. Now, let's see here. In part B of this question, the required is find the rolling frictional force, the force rolling friction. So, once again, I want to solve a force. So that is a dynamics quantity, forces. And it really leads us to the most important equations in physics, the heart of solving so many dynamics problems. We write down Newton's second law. All right? I'm telling you right now, if you sometimes are stuck on an assignment or test on exams like this is a dynamics problem, I don't know what to do, just write down these two equations. These two equations are the key to solving many dynamics problems right here. We do it over and over and over again. Here is the heart of solving so many dynamics problems. So we write down F net equals ma, and then F net is the sum of all forces acting on the object, which in this case is the rolling frictional force, the force of gravity, and the normal force. And as we've done so many times, force of gravity and normal force cancel out because they're equal in magnitude, but opposite in direction and acting on the same object. Gone. So what do we have left here? We have left that the net force is equal to the force of rolling friction. That's the only thing left. So I can bring this consequence over to here and say, well, F net is force rolling friction, and it is equal to ma. I've just made the replacement there, just made the substitution. And that leads us to substitution, where we can plug in the numbers. Force rolling friction is equal to the mass of the object times the acceleration it's undergoing. Negative value, it's slowing down. I plug in my numbers and I get a solution here. Force rolling friction is negative 1.4 times 10 to the 4 newtons. So that's quite a bit of uh, deceleration. All right, so now we're on to part C of this. Now let me warn you, this is a completely different question. The type of friction is completely different because now the car is skidding. The wheels lock up and you're going to lay some rubber on the road. Okay, so let's draw a free body diagram here. The weight, force of gravity on the object is here. We're on the planet Earth. It's on the road, so there's a normal force. And now is the force of kinetic friction. What else do we know? We know by looking up on page 101 that the coefficient of kinetic friction is 1.07, a unitless quantity. The mass of the car is still the same from the previous one. The initial velocity before we start stopping is still the same. And the final velocity is going to be 0 because we want to stop. All right? And what we want to now do here is they're asking us to solve for three different things. They're asking us to solve for the force of kinetic friction, the acceleration that the car undergoes as it's coming to a stop, and the displacement. How far does it move forward while it's stopping and then eventually coming to a stop? So these are the three requirements we have in part C. So the first one, we need to find the force of kinetic friction. Well, if I'm given the coefficient of kinetic friction, mu k, that's a pretty good hint to me. I've been given the coefficient of kinetic friction. I bet you they're wanting me to use this equation right here. And that would be true. So the magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the magnitude of the normal force. Next line, we know that the normal force is equal in magnitude but opposite in direction to the force of gravity, so we make that substitution. And eventually we plug in what the force of gravity is equal to, what the expression for it is, mg, and we plug that in. Now these are all known quantities, so we can substitute. And that's exactly what we do. We substitute in the values and we get a force of kinetic friction, the magnitude of it anyways, right? Because that's all this is allowing to solve. And then the direction here, the direction comes from looking at the free body diagram. And as usual, frictional forces are always in the direction opposing motion. Usually you're moving forward positive and friction acts backwards negative. So this came from the free body diagram right there. Next, they want us to calculate the acceleration of this car as it's skidding to a stop. kinetic friction. Well, I'm not given a lot of kinematics information. I know the initial velocity, but I know the final velocity, but I don't know how much time it took to stop. I don't know how much distance it took to stop. So kinematics will not lead us to solving for this acceleration. But I am given a lot of information about the forces. So that's going to tell me, it's a hint that probably the best way to proceed here is through dynamics equations. So, as I've said many times, that most important equation in physics, F net equals ma, you write it down. You write down F net is the sum of all forces, you write it down, okay? And in this case, it's the force of kinetic friction because the object is sliding. And as always, the force of gravity and the normal force cancel out. So that leads us to the consequence that the net force is equal to the force of kinetic friction. It's the only force left over. So we can use that. We bring it over to here. We substitute in for net force as the force of kinetic friction. We do a little rearranging of this equation right here. And then we substitute. We know the force of kinetic friction. We calculated that in the previous part. We know the mass, and we have an acceleration of negative 10.5 meters per second squared. So now we have calculated the acceleration. And what do we have here? Well, this is the last portion of part C. The last portion of part C. And they want us to find the displacement. How far forward does this car move while it's coming to a stop? So this is definitely a kinematics quantity. So we're going to have to use a kinematics equation. And I know it's going to come to a stop, so I know final velocity. I know the initial velocity, I'm told that. And through my work in dynamics, I was able to find acceleration, calculate it, bring it over here into a kinematics equation. That's why we need to understand this relationship between kinematics and dynamics with the use of acceleration, sort of bridging the two. So this is the equation to use right here. I now know all those values, so I can substitute them, plug in the values, and I get a displacement of positive 34.2 meters. And we've solved for it. That's great. Okay, so part D says, hey kids, let's do this whole thing all over again, except it won't be on dry asphalt. Nope, not going to happen. We want it on ice. So here is rubber on ice, 0.005. All right, totally different. So you would repeat all of this all over again. You would repeat it all over again, except you would not use the coefficient of kinetic friction 1.07 for rubber on asphalt. You would use the coefficient of kinetic friction for rubber on ice. So this would be replaced with 0.005. And then you would go through this question again. You see how the value would change here, which would lead to a change in the force of kinetic friction, which would then lead to a change in the acceleration, and would then lead to a different value for uh, displacement. So I'm going to leave you to try that on your own. I'm going to leave you to try that on your own because the structure is right here, kids. I know you can handle this. And then E said, in the skidding test, does the mass of the car have an effect on the average acceleration? Explain using examples. So try to analyze what you've done there and see if you can answer question 8E. Also, I'm going to give you a homework question. I just did for you practice question 8. And I've shown you how to go through a similar question with the sample problem. I now want you to try practice question 7. Let's see if we can answer practice question 7. That'll be your homework. All right, be patient with yourself. If you have questions, ask me. Please put them in the question discussion thread area. Be happy to answer them for you. And have a great day. Stay safe. All right, wash your hands, and we'll see you tomorrow. Bye-bye.